All right, another video, still talking about limits here, but we are moving on from 2.5 to section 4.5, where we learn about this rule called L'Hopital's Rule. L'Hopital, named after a French mathematician, Guillaume de L'Hopital, although maybe it shouldn't be. Fun fact, L'Hopital had an agreement at one point with another mathematician, Johann Bernoulli, and where L'Hopital paid Bernoulli money, and Bernoulli gave L'Hopital his discoveries. And then L'Hopital published them, and so L'Hopital's rule is named after L'Hopital and not Bernoulli, even though most historians think that Bernoulli, or know that Bernoulli came up with this rule in the first place, and just gave it to L'Hopital because L'Hopital had enough money to pay Bernoulli for it. Anyways, you don't care about any of that. L'Hopital's rule. What L'Hopital's rule allows you to do is evaluate limits. Like, evaluate limits, I'm good with that. I did that in 2.5. Right, but L'Hopital's rule is a more powerful way of evaluating limits. You could go back and redo all the 2.5 questions that I asked you using L'Hopital's rule once you learn it. But what you'll see is I'm going to introduce a variety of new problems in 4.5 that you would not have been able to use the methods of 2.5 to solve. So this kind of continues along with what we were doing evaluating limits, but it gives you another tool, a tool that will allow you to answer more difficult questions than you could going into this section. So what L'Hopital's rule says is this. It says that if you're evaluating a limit, and the limit is of this form, so f of x over g of x, I'll make that more clear as we go on. And that happens to be what's called an indeterminate form. So if you have an indeterminate form, and you're probably wondering what the hell is an indeterminate form, I'm going to save that for now. The short answer is an indeterminate form are the types of questions that you've been asked so far in this class. But I want to make that a little bit more precise because if you don't have an indeterminate form, you can get a wrong answer using L'Hopital's rule. This deserves a video, just not this video. So if you have an indeterminate form, and don't worry, more on that later, then when you're trying to evaluate a limit and you're having a hard time, what you can do is take the derivative of the top of the fraction and the derivative of the bottom of the fraction. The short version of L'Hopital's rule is what's inside the box here. It says, somewhat surprisingly, that when you're evaluating a limit, you can involve calculus 1. You can take the derivative of the top and the bottom of a fraction. And you're like, wait a minute, taking the derivative of a fraction, I learned about that in Calculus 1. You got to use the quotient rule. Now, that's not what L'Hopital's rule is saying. L'Hopital's rule is saying when you're trying to evaluate a limit, and that limit ends up kind of being the limit of something of a fraction, which, as a reminder, is kind of what all the problems we've seen so far have looked like, then it turns out that you can find the answer to that question by finding the answer to a different question. That different question being a different limit. And often that other limit is easier to evaluate. Okay, this needs an example. Let's start with an easier example. Suppose somebody asked you to figure out the limit as x approaches infinity, sure, of 2x over x. All right, say you're trying to figure this out. This is a fairly easy question. You probably wouldn't even need L'Hopital's rule for it. You might just recognize that the x's can cancel out and that this limit is equal to the limit as x approaches infinity of 2 over 1, which is just 2. So the answer is just 2, and that's all true. But I want you to think a little bit about why that's true. This answer is equal to 2. That's 100% correct. But that might be a little bit surprising because if you just think about the top and the bottom of the fraction, the x is getting arbitrarily large. So 2 times some number that's getting arbitrarily large is arbitrarily large. You kind of think about the top as going to infinity, but the bottom is going to infinity also. So you have this fraction where the top is, informally speaking, infinity, and the bottom is infinity. So I'm dividing something by itself. Shouldn't the answer just be 1? Or like undefined because infinity over infinity is really weird, right? You're like, no, that's not the right answer. Okay, you're right, that's not the right answer. But can you see how that would be a little bit confusing that infinity divided by infinity is going to end up being equal to 2? Well, we can justify that. And the way we can justify that is sort of thinking about a graph. If you just graph y equals 2x, thinking like y equals mx plus b, it's a straight line, it goes through the origin, it's got a slope of 2. So sure. Y equals 2x. And then you just graph y equals x. So same thing, it's y equals mx plus b. It goes through the origin. Now it's got a slope of 1. Here's y equals x. As my x value goes to infinity, if I go way out to the right on the graph, this height gets arbitrarily big and this height gets arbitrarily big, which is where I was getting the infinity over infinity idea that I was talking about. But if we're evaluating this limit, this one is higher than this one at any given point. Right? You pick whatever your favorite x value is. X equals, I don't know, 4 maybe. The height of this graph at 4 is exactly 4 because the y value is always the same as the x value. the height of this graph when x equals 4 would be 8. And that's because the y value here is twice whatever the x value is. And there's nothing special about 4. That's true at any x value. This height is always twice as big as this height. So even when x gets arbitrarily large, the height of the top thing will always be twice as big as the height of the bottom thing. So we can kind of resolve this infinity over infinity paradox by thinking about, yeah, they both get to infinity eventually, loosely speaking, but the top one gets there kind of twice as quick, right? Because this slope is twice as big as this one, this gets there twice as quickly as this one gets there. Wait, the speed at which this thing approaches infinity? I know about the speed at which things change. I took a whole course learning about the speed at which things change. It was Calculus 1, right? What the derivative is the rate of change. So it kind of makes sense that I can use derivatives when I'm evaluating limits where it appears that I get an infinity over infinity case, but really one is, informally speaking, getting to infinity quicker than the other one. How do I measure getting to infinity quicker than the other one? Well, derivatives let me measure the speed of change. If you were asked this question, if you were asked to figure out the limit as x approaches infinity of 2x over x, and you didn't want to immediately just cancel these x's right here and say that the answer is equal to 2, what you could do is recognize that this is an indeterminate form. Again, more on that in the next video. And then say, because it's an indeterminate form, I can use L'Hopital's rule. And typically when you're using L'Hopital's rule, you don't just write an equal sign, you write an equal with a little h on top. Little shout out to this guy L'Hopital, who didn't even invent this rule, but whatever. Put a little equal sign with an h on top just to tell the reader that, hey, the reason this limit's equal to the next limit is because I'm applying L'Hopital's rule. This limit is the limit as x approaches infinity. And then what L'Hopital's rule says is if you think about just the top of the fraction as a function, so f of x equals 2x, and the bottom of the fraction is a completely separate function, g of x equals x, then this limit is equal to the limit as x approaches infinity still, I keep my limit the same, f prime of x. What's the derivative of 2x? It's just 2. What's the derivative of x? It's just 1. I get that same answer of 2 using L'Hopital's rule. And you're like, that's really, really stupid. Why would I ever do that? It's way easier to just cancel out the x's. Okay, let me try to make a better argument. What if I asked you, maybe this is example 2, if this were example 1. The limit as x approaches infinity of 2x plus 1 divided by x plus 3. Sure, I can ask you this question. 2 times an infinitely large number plus 1 more ends up being infinitely large. An infinitely large number plus 3 ends up being infinitely large. Both the top and the bottom are getting infinitely large, but the top's getting there a lot quicker than the bottom. Right? If I graph these things, this will be the last time that I graph these. You don't need to graph these going forward. It's just supposed to add some intuition for you. If I graph these things, 2x plus 1, it's got a y-intercept of 1 and a slope of 2. So it looks, loosely speaking, like this. Y equals 2x plus 1. And then if I graph my other function, it's got a y-intercept of 3. So 1, 2, 3. It starts out a little higher, but its slope is only 1. And so if I look at small values of x, the bottom is actually higher up than the top. But I'm not concerned with small values of x. I want to know when x gets infinitely large. And if I get way, way, way out here to the right, you see that this graph overtakes this graph. Like, oh, but this is getting confusing. Like, I can't just cancel out the x's here because I have addition in the top and the bottom. How am I ever going to figure out this limit? Well, you got some options, right? You could use the methods of 2.5 to solve this. But if you didn't know the methods of 2.5, you could just use L'Hopital's rule. L'Hopital's rule tells you that this limit is equal to, what's the derivative of 2x plus 1? It's just 2. What's the derivative of x plus 3? It's just 1. This limit is also equal to 2. This plus 1 and this plus 3 didn't even end up mattering because when x gets infinitely large, this is, roughly speaking, twice whatever x is. Yeah, it's 1 more than that, but who cares? 1 more. If x is a billion, this is 2 billion and 1, and this is a billion and 3. It's basically 2 billion over a billion. The plus 1 and the plus 3 really don't matter when x gets arbitrarily large. You're like, all right, I guess I kind of see how L'Hopital's rule works. I'm still not all that impressed, though, because you haven't done anything that I couldn't have done in 2.5. Let me give you one more example, and then we'll call this video good. What if I asked you this question? What if I asked you to evaluate the limit as x approaches 0 of the sine of 3x divided by 6x. Right, the first thing to notice is you'd have no chance doing this with the 2.5 methods. In 2.5, all we looked at were polynomials. We didn't see any trig functions like sine of 3x. You wouldn't even know where to begin if this were 2.5. But the good news is you can use L'Hopital's rule. We can use L'Hopital's rule to solve this. It turns out that this is an indeterminate form. Again, more on that in the next video. And because this is an indeterminate form, all I have to do is take the derivative of the top and the derivative of the bottom. Before I do that, because the purpose of this video is to kind of give you some understanding of these concepts, I want to graph these for you. All right, here's the sine of 3x in red here, and here is 6x in blue here. And what I'm interested in is the quotient of these two functions when they get really, really close to 0. And you might notice that each one individually, when its x value gets close to 0, gets close to 0. So it kind of seems like a 0 over 0 case. You're like 0 over 0, that should be undefined. No, because when we're talking about the limits, really what's going to end up mattering is the speed at which they approach 0. Does this one get closer to 0 quicker, or does this one get closer to 0 quicker? Right? You can kind of see, just looking at the picture, that it looks like the red one gets close to 0 quicker than the blue one gets closer to 0. For any given x value, I mean, I can zoom in if that makes you feel better. For any x value that's really, really close to 0, the red one appears to have a height less than the blue one. But how much less? How much quicker does the red one get to 0 than the blue one gets to 0? Well, L'Hopital's rule can figure that out. The speed at which the red one gets to 0 is just the derivative of the red function. And the speed at which the blue one gets to 0 is just the derivative of the blue function. So what I can do is apply L'Hopital's rule here and say that this limit is equal to the limit as x approaches 0 of, what's the derivative of sine of 3x? So this is where you got to remember what you learned in Math 251. Right? Maybe you remember that the derivative of sine of x is cosine of x, and maybe you recognize that this 3x here makes you have to involve the chain rule. So you take the derivative of the outer function, the sine part, to get cosine, and then you leave the inner function alone, cosine of 3x. But then you're not done. You still have to multiply by the derivative of the inner function. So you get cosine of 3x times 3. And then on the bottom, you would get a 6. What L'Hopital's rule tells me is that this limit is the exact same as this limit. This limit, I can't figure it out. I can't look at this and tell what it is because it turns out it's indeterminate form. This one's not an indeterminate form. How do I know it's not an indeterminate form? Because when x gets really, really close to 0, then this is going to be asking me what is the cosine of a number that's basically 0. And if you have your unit circle memorized, you might remember that the cosine of 0 is just 1. So I have the cosine of 0, which is just 1 times 3, which is just 3, divided by 6. This is just 3/6, in other words, 1/2. It turns out that the limit as x approaches 0 of sine of 3x over 6x is just 1/2. That makes sense. Why is it 1/2? Because at any given point, the numerator here is half as big as the denominator. The red thing is half as big as the blue thing. Right? So it doesn't matter how close I get to 0. When I get infinitely close to 0, you can't even see it because we can't zoom in enough. But the blue thing is twice as tall as the red thing. So the quotient of the red thing and the blue thing is going to be 1/2. Don't believe me? Here it is graphed. Right? If you plug in different values of x, you'll get different values of this quotient. But when the x value gets really, really, really close to 0, the y value gets really, really close to 1/2. Which is why this limit were equal to 1/2 in the first place. This is L'Hopital's rule. Sometimes you use L'Hopital's rule one time and it changes an indeterminate form into a form that is no longer indeterminate, one whose limit I can figure out. Turns out sometimes you don't. Sometimes you do it once and you still have an indeterminate form, so you do it again. Sometimes you have to do it again and again and again. And in order to figure out when I can stop doing L'Hopital's rule, I need to be really good with indeterminate forms. So what I'm going to do is call this introduction good and then make a new video just talking about the subtleties of indeterminate forms. And then once you're an expert there, we'll go back and we'll do L'Hopital's rule again, but more advanced examples. Not these introductory examples where I focus on the understanding, but the advanced ones where you see some pretty hard calculus and algebra going on. But that's all for future videos, so I'm going to call this one good.